So hello, everyone. My name is Tom Gajecki, and I'm a PhD student at the Auditory Prosthetic Group in Hannover, under the supervision of Waldo Nogueira. And today, I would like here to present our submission to the Clarity Challenge under the name of Binaural Speech Enhancement based on deep attention layers. Before I begin, I would like to thank the Clarity team for letting us present our work here in this workshop. And I would also like to congratulate the team for such a nicely organized challenge. So that said, we'll proceed. So here we present a speech enhancement system that is based on end-to-end audio source separation. And the idea is to use a system that connects information between hearing aids. Specifically, we investigate the effect of applying attention mechanisms to improve binaural audio source separation. But what is binaural hearing? So binaural hearing is the ability that the brain has to process information available in the sound of each ear and both sides of the head. Binaural hearing gives us a mechanism called binaural unmasking, which is the ability that the binaural system has to enhance target sound sources when spatially separated from other interferers. The binaural system makes use of two cues: interval time differences, or ITDs, and interval level differences, or ILDs. We can see depicted these two effects. So ITDs have to do with the difference in arrival time of the sound on each side for a sound that is not coming from the front. So the ear lateral to the sound will capture the sound earlier than the ear contralateral to the sound. And similarly, in terms of level differences, interval level differences are the differences in level of the sound at each listening side. And this is caused due to the head shadow that acts as a filter for sounds coming from a certain azimuth. So hearing loss can cause a degradation in the ability of exploiting binaural cues. This can cause poorer speech intelligibility, performance in noisy conditions, and poorer sound localization abilities when compared to a healthy auditory system. So in this work, we aim at developing a speech enhancement system that uses inputs from both hearing sides. The system should share information between sides inspired by the binaural system to exploit potential binaural cues. We propose a deep neural network architecture, which shares information between sides through intermediate layers that we will refer to as attention layers, inspired by other successful attention mechanisms used in other domains. We hypothesize that an algorithm that uses attention layers will yield better objective performance when compared to a system that does not use them. So here again, our architecture is based on a well-known single-channel noise or speech separation system called the TASNet. We've seen already this in this workshop. We have this block diagram, which we already see. This consists of an encoder that takes the audio input and uses a separator to predict the mask that will send the encoded signal to a decoder that produces the resynthesized denoised signal. I will go a bit into detail because I want to define the parameters that parameterize this model, because one of these parameters is going to be investigated in this work. So N is the number of filters using the onto encoder, which is, as previously explained, a one-dimensional convolution layer. L is the number of filters and samples. So this is the number of samples that the model will be looking at to predict a given mask. B is the number of filters in the bottleneck that is contained inside the TCN or temporal convolution. S is the number of channels in the skip connections. So each of these blocks is more clearly explained here, more in detail. And the output actually has two outputs. One is the residual paths that will serve as input for the next convolutional block. So this will be this path here. And the skip connection, which is the ones that go out from the sides here. Then we have the number of channels in the convolutional blocks here. As we can see, this convolutional block will end up with you having 8 channels, and the kernel size of the depth convolution, the kernel size is P. Then we have X, which is the number of convolution blocks in each repeat. That is the number of colored blocks in each column. And R will be the number of repeats. That is the number of columns in the model. I'll say now that the parameter we're going to investigate is S, so the channels in the skip connections. So because in this challenge we're dealing with 2 hearing aids, we have to use two of these models, one in each hearing side or each listening device. In this case, we will investigate the independent model. That is called independent because each of these models will be applied to each hearing aid, but they will be independent from each other. They will perform their processing without talking to each other, let's say. Another model that we investigate and we propose is the single attention model. This model uses an attention layer up to the TCN. And the output of this layer will be introduced to the masking block of each of the sides. And the next and last model that we investigate is the double attention model. And it's called this way because it uses two attention layers, one after the encoder and one after the TCN. Now, so what do these attention layers do? So these layers actually produce, perform element-wise dot product to each latent representation of the signals in each side. And it's mathematically represented by this really simple expression. So if we have two matrices, let's say lambda 2 and delta 2, we can transmit information and produce and multiply all the elements contained in these matrices together. The output will be a matrix, the same dimensionality of these two, and the output of this attention layer will be introduced to the TCN. The same exact mechanism or same operation will be done for attention layer 1. The code to implement this model shown in this figure is implement TensorFlow and is available in the link below if you're interested in reproducing our results or have fun changing some parameters that are available. So these are the hyperparameters we use for our models. So we use 64 units, filters, sorry, in the encoder and decoder. The number of samples we're looking at per masking estimation is 16. Number of channels on the bottleneck is 64. As I said, the number of channels on the skip connections is S and is variable. And I will define it a bit later. So we'll leave it as S for now. The number of channels on the convolution block will be 64 and it will be of size 128. We use 2 convolutional blocks per repeat and 2 repeats in total. Note that the latency or the algorithmic latency introduced by the algorithm is defined by this value here, the number of filters and the encoder, and it's 16 samples, which corresponds to 2 milliseconds for an input signal sample at 8 kilohertz, which is the sampling frequency we used for the challenge. So the training, we trained 8 different models for 8 different S's, 4, 8, 16, 32, 128, 256, 512, and 1024. Each model was trained 5 times to account for variance related to the random initialization. The models were trained for a maximum of 100 epochs, using early stopping with a patience of 5 epochs, looking at the validation set. 4-second long audio sections corresponding to the front microphone, that is the channel number 1 in the data set provided by the Clarity challenge, resampled at 8 kilohertz were used for the training. The learning rate was half if the accuracy of the validation set did not improve during 3 consecutive epochs. And for the optimization, Atom was used to maximize the scaling invariant source to noise ratio, explained in the previous talk. And these are the results. So in this box plot, we can see in the x-axis the factor that we investigated, which is the number of filters and the skip connections, which ranges from 4 to 1024, as I just said. On the y-axis, we have the SI, SNR, and dBs. This is the amount of noise reduction applied by the algorithm. Here, the greater the value, the more noise reduction applied. And we can see from this, and I must say also that the colors of the different colors correspond to the different models. We have the red one corresponds to the dependent model, the green one to the single attention model, and the blue one to the double attention. In general, we can see a trend upwards, proportional to the number of filters in the skip connections. Arriving to like a threshold of 128 filters, above which it seems to decay a little bit. Also, we can see that for each specific size of the skip connection, the specific number of filters, we see that the more attention we apply to the model, the higher the performance, let's say. And here's important also to know that because the attention layers produce just a multiplication, these models have all the same number of parameters. Regarding the MBSTOI results, here this is for the validation set, so for the second round. And so we have the number of filters and the skip connections for all the rows. And in the columns, we see the baseline, the independent model, the single attention model, and the double attention model. We can see that the results, the MBSTOI results, don't follow the same trend as the SI SNR. So this doesn't seem to be a correspondence with the number of filters and the actual performance on MBSTOI. However, we highlight here the high score we got out of the 5 trained models, and it corresponds to a double attention model with 512 filters in the skip connections. For the test set, here are the results for the baseline, for the speech and noise conditions, speech and noise interference. For the baseline, we have 0.34, and for a submitted algorithm, we have 0.55 for the speech interfere, and for the noise interfere, we have for the baseline 0.29 and for 0.48 for the submitted algorithm. Due to some problems we had in the submission for the audio files for the speech tests, we had a poor performance on the baseline, so we won't report this here. So to conclude, in this work, we performed a binaural speech enhancement method based on deep binaural attention layers. The noise reduction amount seems to be proportional to the number of attention layers, being significantly higher using a double attention system when compared to a non-attentive one. We observed a threshold above which larger attention size yields poor performance. And for future work, we think that other attention mechanisms, such as additive attention, should be investigated to reduce potential computational cost. So that's all from my side. I hope you enjoyed the talk and looking forward for feedback and questions. Thanks a lot.